Welcome to our deep dive into Kotlin Coroutines and the powerful withContext function. In this video, we'll explore how withContext enables efficient context switching within coroutines, allowing developers to run code blocks in different thread pools without launching new coroutines. Whether you're building Android apps or server-side applications, understanding withContext is essential for writing performant, readable, and maintainable code. We'll start by breaking down what withContext is, then move on to its key characteristics, internal workings, and practical use cases. By the end, you'll have a clear grasp of how to leverage withContext for optimal thread management and structured concurrency. withContext is a suspending function in Kotlin Coroutines that allows you to switch the coroutine's context, such as moving from the main thread to an I/O dispatcher. This function temporarily changes the execution context for a block of code and returns its result once finished. Unlike coroutine builders like launch or async, withContext doesn't create a new coroutine. It simply suspends the current one, runs the block in the specified context, and then resumes in the original context. This makes it an efficient tool for handling tasks like network requests or file operations without blocking threads. Let's highlight the main characteristics of withContext. First, it enables context switching, allowing you to run code in a different dispatcher such as Dispatchers, I/O for I/O tasks or Dispatchers, Default for CPU-intensive work. Second, it suspends the current coroutine without blocking the thread, making it highly efficient. Third, it doesn't launch a new coroutine, keeping overhead low and simplifying lifecycle management. These features make withContext ideal for tasks that require temporary context changes, like database access or network calls. Here's a practical example of context switching with withContext. Suppose you need to perform a long-running task, such as fetching data from a network or reading from a file. You can use withContext Dispatchers, I/O, to ensure the operation runs on a background thread, preventing the main thread from being blocked. Once the task completes, execution returns to the original context. This approach is especially useful in Android development, where keeping the UI thread responsive is crucial. One of the most powerful aspects of withContext is its ability to suspend the current coroutine without blocking the thread. When you call withContext, the coroutine pauses execution, switches to the specified context, and resumes once the block completes. This suspension is lightweight and doesn't tie up system resources, making it perfect for asynchronous operations like network requests or database queries. The coroutine resumes in the original context, ensuring seamless workflow. Unlike launch or async, withContext does not create a new coroutine. Instead, it reuses the current coroutine, simply altering the execution context for the block of code. This keeps the overhead low and avoids the complexity of managing multiple coroutine lifecycles. It's a straightforward way to handle context-specific tasks, such as switching to Dispatchers, Default for CPU-intensive work, without launching additional coroutines. Let's look under the hood at how withContext works internally. The function signature takes a coroutine context and a suspending block. It checks the current and new contexts, merges them if needed, and ensures the new context is active. If the contexts are identical, it runs the block without dispatching. If only context elements change, it updates the thread context temporarily. If the dispatcher changes, it dispatches the coroutine to a new thread pool. After the block completes, withContext returns the result and resumes the coroutine. Function signature for withContext is public suspend fun t withContext context, coroutine context block, suspend coroutine scope. T. The context parameter specifies the new coroutine context, such as a dispatcher or additional elements. The block is a suspending lambda that executes in the new context and returns a value of type T. The contract ensures the block is called exactly once, optimizing for inlining and preventing unintended side effects. withContext uses suspend coroutine unintercepted or return to suspend the current coroutine. The lambda inside handles the continuation, which represents the state of the suspended coroutine. This mechanism allows the coroutine to be resumed after the block finishes executing. The old and new contexts are determined, and the new context may include a different dispatcher or thread local variables. This ensures the block runs in the correct environment. Before executing the block, withContext checks if the new context is active using ensureActive. If the context has been canceled, a cancellation exception is thrown. This step is crucial for maintaining structured concurrency and preventing operations from running in a canceled context. It's a safety mechanism that ensures only active coroutines proceed with their tasks. If the new context is exactly the same as the old one, withContext takes the fast path. It creates a scope coroutine and executes the block without dispatching to a different thread or thread pool. This minimizes overhead and ensures the block runs efficiently in the current context. It's used when no context switch is necessary, making the operation quick and seamless. If the dispatcher hasn't changed but other context elements have, withContext uses undispatched coroutine. The block runs in the same thread, but the thread's context is temporarily updated. Once the block finishes, the context reverts to the original. This approach is efficient for tasks that require context changes without thread switching, such as updating job metadata. When the dispatcher changes, withContext follows the slow path. It creates a dispatch coroutine, dispatches the block to a new thread pool, and starts execution in a cancelable manner. This is used for tasks that need to run on a different dispatcher, such as moving from Dispatchers.Default to Dispatchers.IO. The coroutine suspends until the result is available, then resumes in the original context. Once the block completes, withContext returns the result to the suspended coroutine. The coroutine resumes execution from where it left off, now with the result of the block. This seamless transition ensures that tasks like network calls or file operations can be handled efficiently, with results available immediately for further processing. Summarize the steps withContext takes. First, it checks the current and new context to determine if a switch is needed. Second, it ensures the new context is active. Third, it takes the fast path if contexts are identical, running the block in the current context. Fourth, it takes the fast path if only context elements change, running the block without switching threads. Fifth, it takes the slow path if the dispatcher changes, dispatching to a new thread pool. Finally, it returns the result and resumes the coroutine. Dispatchers play a critical role in withContext. They define the thread or thread pool where the coroutine runs. For example, Dispatchers.IO is used for I/O operations, Dispatchers.Default for CPU-intensive tasks, and Dispatchers main for UI updates. By assigning the right dispatcher, you ensure tasks run in their optimal environment, improving performance and preventing main thread blocking. Dispatchers prevent blocking the main thread, ensuring smooth application performance. By shifting heavy or long-running tasks to background threads, you keep the UI responsive and avoid sluggishness. For example, withContext, Dispatchers.IO is perfect for network calls or file operations, while Dispatchers.Default is ideal for computations. Using withContext improves code readability and structure by clearly separating concerns. You can assign specific contexts for tasks, such as UI updates or I/O operations, making the code easier to understand and maintain. This separation ensures tasks run in their appropriate thread, reducing errors and enhancing maintainability. withContext allows you to match task types to optimize thread pools, maximizing CPU and thread utilization. For example, heavy computation tasks can be run on Dispatchers.Default, which uses optimal CPU cores. This approach prevents overloading any single thread and ensures efficient resource usage, leading to faster and more reliable applications. withContext helps avoid accessing shared resources directly from the main thread, ensuring thread-safe operations. By running tasks in the appropriate dispatcher, you minimize the risk of race conditions and data corruption. This is especially important in multi-threaded environments, where proper thread management is crucial for application stability. Structured concurrency is a key principle in Kotlin Coroutines, and withContext supports it by ensuring the coroutine's context remains linked to its parent. This linkage allows for proper cancellation and error propagation, making it easier to manage complex workflows and maintain application stability. withContext simplifies threading logic compared to manual thread management. Instead of writing complex code to switch threads and handle synchronization, you can use withContext to handle context changes seamlessly. This reduces boilerplate and makes your code cleaner and easier to maintain. Let's compare withContext with launch and async. withContext suspends the current coroutine and executes sequentially in the new context, returning the result directly. Launch creates a new coroutine for background tasks that don't need a result, providing a job to track. Async launches a concurrent coroutine and returns a deferred T for retrieving the result later using await. Each has its own use case, and choosing the right one depends on your task requirements. withContext executes sequentially in the new context, suspending the current coroutine. Launch and async, on the other hand, launch concurrent coroutines that run independently. This difference is important when deciding how to structure your code, especially for tasks that require immediate results versus those that can run in the background. withContext returns the result directly, making it ideal for sequential tasks. Launch doesn't provide a direct result, only a job for tracking completion. Async returns a deferred T, allowing you to retrieve the result later using await. Understanding these differences helps you choose the right coroutine builder for your needs. Use withContext for sequential tasks where you need the result immediately, such as switching to an I/O or computation context. It's perfect for operations like database access, network requests, or CPU-intensive calculations that require context switching, but don't need to run concurrently. Launch is best for background tasks that don't need a result, such as logging or sending notifications. It creates a new coroutine that runs independently, allowing you to track its completion with a job. This is useful for fire-and-forget operations where the outcome isn't critical to the main workflow. Sync is ideal for parallel tasks where results are required, such as aggregating data from multiple sources. It launches a concurrent coroutine and returns a deferred T, allowing you to retrieve the result later using a wait. This is perfect for scenarios where multiple tasks can run in parallel and their results are needed for further processing. Exception handling with withContext is straightforward. Exceptions are automatically propagated to the parent coroutine, ensuring proper handling and maintaining structured concurrency. You can use try-catch within withContext to manage exceptions locally or handle them globally in the parent coroutine. This flexibility allows for robust error management in complex workflows. If an exception occurs within withContext, it is thrown to the parent coroutine for handling. This automatic propagation ensures that errors are managed at the appropriate level, preventing silent failures and maintaining structured concurrency. It's a key feature for building reliable applications. You can use try-catch within withContext to handle exceptions locally. This is useful for tasks like network requests, where you want to show an error message to the user if something goes wrong. By catching exceptions within the block, you can provide specific error handling and improve user experience. Exception handling can be tailored based on the dispatcher or task context. For example, you might handle network errors differently from database errors, depending on the context in which the exception occurs. This approach allows for more granular error management and better application stability. Let's look at a real-world example of local exception handling with withContext. Suppose you're fetching user data from a server. You can wrap the network call in a try-catch block within withContext, Dispatchers.Default, catching exceptions like network timeouts and displaying an error message to the user. This approach ensures that errors are handled gracefully and users are informed of any issues. Another real-world use case is propagating exceptions to the parent coroutine. For example, in a payment processing workflow, you might validate payment details, process the transaction, and send confirmation, each in its own withContext block. If any step fails, the exception is propagated to the parent coroutine, allowing you to handle errors globally and inform the user of the failure. In the fetch user data example, a simulated network call is wrapped in withContext, Dispatchers.Default. If the call fails due to a timeout, the exception is caught and an error message is displayed. This pattern is common in real-world applications, where network reliability can't be guaranteed and user feedback is essential. In a payment processing workflow, multiple steps are handled in separate withContext blocks. Validation, transaction processing, and confirmation are each run in their appropriate dispatcher. If any step throws an exception, it's propagated to the parent coroutine, allowing for centralized error handling and user notification. This approach ensures robust workflow management and clear error reporting. The simulated server function demonstrates how withContext can be used for network operations. By introducing a delay and throwing an exception, you can test error handling and ensure your application responds appropriately to failures. This is a valuable technique for building resilient applications. In the payment workflow, validating payment details is handled in withContext, Dispatchers.Default. If validation fails, an illegal argument exception is thrown, which is then propagated to the parent coroutine. This ensures that invalid payments are caught early and users are notified promptly. Transaction processing is handled in withContext, Dispatchers.Default, ensuring CPU-intensive work runs on optimal cores. If an exception occurs during processing, it's propagated to the parent coroutine for handling. This separation of concerns improves performance and reliability. Sending confirmation is handled in withContext, Dispatchers.Default, ensuring the operation runs on a background thread. If an exception occurs, it's propagated to the parent coroutine, allowing for centralized error handling and user notification. This approach ensures that confirmation messages are sent reliably and errors are managed effectively. Recap: withContext is a powerful tool for context switching in Kotlin Coroutines. It enables efficient thread management, improves code readability, and supports structured concurrency. By understanding its internal mechanics and practical use cases, you can write performant, maintainable, and robust applications. Remember to use withContext for sequential tasks, launch for background operations, and async for parallel tasks requiring results. Let's visually recap the key concepts. We've seen how withContext enables context switching, suspends coroutines without blocking threads, and returns results directly. We've also explored exception handling, dispatcher roles, and real-world use cases. These concepts are essential for mastering Kotlin Coroutines and building high-performance applications. Here are additional visuals to reinforce your understanding. These diagrams illustrate context switching, dispatcher usage, and exception propagation in Kotlin Coroutines. By studying these visuals, you'll gain a deeper insight into how withContext operates and how to apply it effectively in your projects. Let's look at more visual examples from real-world scenarios. These images show how withContext is used in various workflows, such as payment processing, network calls, and UI updates. Visualizing these examples helps solidify your understanding and prepares you to implement withContext in your own code. Congratulations on completing this comprehensive guide to withContext in Kotlin Coroutines. You now understand its purpose, internal mechanics, and practical applications. By leveraging withContext, you can write efficient, readable, and robust code for a variety of tasks, from network operations to UI updates. Keep experimenting with different dispatchers and exception handling strategies to master coroutine context management. Happy coding!